this is August 2021, Rington Fields number 2, RF2. We're given z mod 3 kind of 0, 1, minus 1. We're given a polynomial, and then we define x plus the ideal generated by g, I guess. Yeah. And then we have k, which is the polynomial ring of z3, mod out that ideal. Okay, so the first one is we want to show part A. Show A is irreducible, and it is the minimal polynomial of alpha, where alpha is this guy. So letting an alpha be the minimal polynomial, and then just evaluating g at alpha, we will see plugging in, we can distribute and move the ideal out, move our coset out. This is just g, so it's going to get absorbed, giving us the identity coset, i.e. 0. So alpha is indeed a root of g of x. Since alpha is a root, that means our minimal polynomial divides g, so we can factor g into the minimal times some other polynomial. If h has a degree of 1 or more, or 1, then that means the degree of alpha, or the minimal polynomial for alpha, is also equal to 1. And that's not good, because that would mean that the minimal polynomial is just linear, so alpha would have to be in z3, but just plugging in 0, 1, negative 1 into g, you don't get 0. So that's a contradiction. That means that h cannot be 1, it has to be 0, i.e. the minimal polynomial of alpha is just g of x. So g of x is irreducible as well. Okay, part B is showing that k is isomorphic or is equal to z3 adjoin alpha. So we're just going to define or give let phi be our, oh, it has a word. Oh, I forgot what the word is. It's the evaluation map, there we go. So we let phi be our evaluation map, where we just evaluate the polynomial at alpha, and then we're going to take f to be in the kernel of phi. So when we do that, f is 0, obviously. We know then that alpha is a root of f because it's in the kernel. F is in the kernel. So then our minimal polynomial g has to divide f, and if our minimal polynomial g divides f, then that means f is in the ideal generated by g. So then our kernel of phi is a subset of the ideal generated by g, but we already know g is in the kernel because everything in g is a root of alpha. So therefore the kernel is the ideal generated by g. So then when we, by the first isomorphism theorem, when we mod out by our kernel, this is just k. And then we have the degree extension, yeah. So the extension of k over z3 is the degree extension of z3 join alpha over z3, which is the degree of alpha, which is 2, because the minimal polynomial of alpha is g and is quadratic. This is a totally different vibe presenting with it all up already. Okay, so then part C, showing that it's a splitting field over 3, yeah, C3. Okay, so we want to show it's a splitting field, so we have to have the other root in terms of alpha. How do we do that? Well, we already know that alpha is a root, so we come up with this relationship where alpha squared is equal to alpha plus 1. And then you can do this, I show it explicitly to the right, but you can get some algebra to show that we have this. So yeah, because that would just be powers of alpha. So what would it be? I don't know, it's fine. Okay, so if we're looking at negative alpha to the minus 1 and evaluating it in the polynomial, each step of the way. This step, after we found our common denominator, we just get the minimal polynomial evaluated at alpha again, so we get a 0 on top. Cool. So then we can express this root as either -1 over alpha or 1 minus alpha, also works the same, given by that relationship. And then part D, alpha does in fact generate the multiplicative group for k cross. Alpha is itself, alpha squared, and then just going through step by step, you get that its order is 8 and it generates the whole group because we just don't have 0. All right.